Welcome, everyone. This is the first of a series of lectures that the Division of Physical Sciences is going to do as honoring our 50th anniversary of UCSD. Today, our speaker is Tom Murphy. He went to school and did his PhD work at a small technical institution in Pasadena, California. He also went on to do postgraduate work at the University of Washington in astrophysics, some of which overlaps with what he's going to talk about today. He's both in physics and in the Center for Astrophysics and Space Science. So without further ado, thanks to Tom for agreeing to do this and kick us off for the season.
Okay, thanks, Mark. So first of all, I'm going to give you a little background, somewhat literally, because this forms the screen background for all the slides. So I'm going to explain what's here. We can measure the distance between the Earth, pictured here in the foreground, and the Moon, shown here, using a laser, which we see propagating from the telescope that we're launching out of in New Mexico. And using this, we can measure the distance to the width of a paperclip, which is shown here. No, not that guy. There, that's much better. Okay. And we're doing this as a test of general relativity. Einstein's most impressive achievement was not his E equals mc squared, but understanding how gravity works and as a property of the geometry of space-time and its curvature. So we'll get into that. I'll also tell you about some surprises along the way, like, for instance, the fact that the reflectors sitting on the Moon appear to get sick during full moon and don't respond as well. And at first we thought this was some just bad luck, bad weather, or just happening to come on full moon nights. And we started calling it the full moon curse and, you know, all the werewolf jokes and all this stuff. But it turned out not to be so funny. It's real. Now we think it's more something to do with dust, but there could still be a werewolf involved somewhere. And also, we have found a long-lost Soviet rover, the Lunokhod 1 rover, that had not been seen for 40 years. So I'll describe that as well. Just to motivate that, somewhere on this slide, which spans about a kilometer, a little less than a kilometer from left to right, Lunokhod 1 is somewhere here. Okay, so as a hint, it looks like this, and I haven't covered it up. So we spent a couple years actually looking for this rover. So, you know, I know what it's like to be searching and not finding it. I'm going to not point it out right now because I think you can wait 40 minutes. We waited a few years, and I'll show you later if you didn't manage to find it. Okay, so what is this business about Einstein's gravity? We all know something about Einstein. He's a very popular figure, maybe the quintessential genius. But how many people know what he actually said and what he thought? So one of the things he first tinkered with in his mental experiments was what would happen if you're traveling at light speed and you turn on your headlights? I mean, he didn't think of it in those words, but that's effectively what he was contemplating. And he wanted to believe that any observer, any person, any physicist or experimenter is in an equally valid frame as long as they're not being accelerated. So if you're cruising along at light speed, you should be able to perform experiments, get the same answer as anybody else, so your light should work normally. So what he did, along with the help of others, he wasn't alone, worked out the mathematics behind this supposition, that the speed of light is something inviolate in the universe. So his inevitable conclusion was that space and time are all mixed up. One person's space becomes another person's time. Now, I'm not going to dwell on mathematics here, but I did put for the bold among you the mathematical transformations associated with this ability to go from one frame to another, so that one person's time, this t prime, is a combination of another person's time and space, x. And their space is a mixture of another person's space and time. So that's just sort of the mathematical appearance of how space and time are mixed up. So things like simultaneity and the sanctity of space being different from time are all messed up in special relativity. And this is something that gets tested daily in experiments around the world. this stuff actually works as described by special relativity. So the next piece Einstein thought about was the principle of equivalence. And it's been known for a long time that different objects fall at the same rate in a gravitational field. So a penny and a quarter will fall at the same rate. A bowling ball and a golf ball will fall at the same rate. Even a hammer and a feather, if you can get rid of the air, will fall at the same rate in a gravitational field. So this is a very fundamental relationship in science, and it suggests an equivalence between two types of mass, inertial mass and gravitational mass. Inertial mass is how hard it is to move something, to push a car, for instance, to get it moving, to accelerate it. Gravitational mass is how attractive something is to gravity. So if you put it on a scale, how much does gravity pull down on it and compress it into the scale? So the fact that these two are equal means that for a massive object, gravity pulls on the massive object more strongly, but it's also harder to get it moving. And so the net effect, it cancels out. Anything you drop will fall at the same rate. Okay, so Einstein took that a little bit further, and I have here a clip that was aired on a NOVA program.
In one of Einstein's famous thought experiments, he realized that gravity and acceleration appear to be the same phenomenon. Think about what would happen if an elevator suddenly went into a free fall. The person inside would effectively weigh nothing. Next, imagine that same person in a motionless rocket ship, so far from Earth that the force of gravity is practically zero. Just like in the free-falling elevator, he would also weigh nothing. Now, put the rocket in motion. As the rocket speeds up, the passenger's weight increases. To him, it feels just as if gravity had planted his feet firmly on the floor. Einstein realized that the force of gravity is just the acceleration that you feel as you move through space-time.
Okay, so it was this connection that what we perceive as gravity and acceleration in a rocket are fundamentally very intimately linked. That was the breakthrough, and it started Einstein thinking about the natural frame of motion would be a freely falling frame, like the freely falling elevator. And once you're forced to be out of that frame by the floor, for instance, you perceive this gravity. That started him thinking about gravity as a consequence of what frame you're in, of what the coordinates are, of your state of motion through space-time. So that led to the next insight, which described gravity as curvature.
If there were nothing in our universe, the fabric of space-time would be flat. But add a mass and dimples form within it. Smaller objects that approach that large mass will follow the curve in space-time around it. Our nearest star, the Sun, has formed such a shape in space-time, and our tiny planet Earth goes along for the ride, staying in orbit around the Sun.
Okay, the depiction there is slightly flawed because we can't draw that in 4 dimensions. And so you might have noticed the Earth hovering over the Sun. Well, that's not really what you should take away from it. What you should take away is that the presence of the Sun or a mass makes a curvature in space-time, and the Earth or whatever object is trying to take a straight path through a curved space-time, and that's what ends up curving it into an orbit. So the key idea then is that masses make dimples in space-time or curvatures in space-time, again, not into some spatial dimension as depicted, but that the heavier the mass, the more curvature results. And that orbits of particles are or bodies or comets or whatever might take unbound orbits or elliptical orbits or circular orbits in this curved space-time. And this really leads to the idea that gravity is just a property of the geometry of the space-time. It's not something intrinsic, some interaction between the two, the attractive mass, the sun, and the planet. It's really that the planet is responding to the local curvature in space-time, and that's all it needs to know for how to move. So that means any two objects will follow the same or similar paths. They will accelerate the same. So this equivalence principle is intimately tied to the idea that gravity and geometry or that gravity comes down to just geometry, curvature of space. Okay, and so this is by far less well known as an equation from Einstein than E equals mc squared, but it's much more profound. This is his most significant accomplishment, that the curvature, how space-time curves, is symbolized by this tensor G, and it's just equal to some multiplier of how much stuff, the mass and energy, put into space-time. So that's his general relativity. And we have to keep in mind, though, that it was really this guy who did the work, a younger Einstein. Most of the pictures are from his older days of fame, but it's really a younger Einstein. And just to confront some of the myths about Einstein's upbringing, he was not a terrible student. Many people like to quote that, but he was actually, it took him a while to get to speaking. He was a little slow to learn to speak, but he was a top student all through grade school. He finished high school by 17. He had a PhD in physics by 27. And even while he worked at the patent office, he was doing physics, communicating with physicists throughout Europe. He was regarded as a real physicist. And at age 26, he contributed 4 major ideas to physics, among which were the idea of a photon as a particle of light, and the special relativity, and E equals mc squared. So, I mean, some big ideas. So, but, you know, talking about curved space-time, it sounds kind of nebulous and a little hokey. It sounds like crazy talk, some sort of gibberish. And it sounds a lot like the emails I often get from people who have better ideas for gravity and want to knock off Einstein. They never, by the way, go after the more obscure people in physics. They never challenge Snell's law of refraction or Euler's equations or Hooke or anybody like this. It's always Einstein, because they were a poor student and so was Einstein, right? So clearly they can compete on the same field. So, you know, how come Einstein is the household name and this guy Joe Shoe-on-Head is not? And the answer, it's hard to avoid the fact that, right, that gets your attention, right? We have experimental evidence that favors Einstein's ideas. In fact, the way I like to put it is we are forced to accept these ideas because the experimental evidence doesn't leave us a choice. Okay, so let's talk some about that experimental evidence. Einstein already knew about one of the key pieces of evidence when he formulated his general relativity, and that is that Mercury's orbit is elliptical, and that ellipse precesses in time. It's a very slow rate, 43 arcseconds per century. It's a very small rate of precession. Nonetheless, as early as 1859, astronomers understood that Mercury's orbit was not well described by Newtonian gravity, given the known planets. Okay, so it's a long-standing, by the time Einstein worked on his general relativity, it was a long-standing problem, this precession of Mercury's orbit. So it's one of the first things that Einstein turned his mathematical machinery of general relativity onto. That's the first problem he attempted to solve. And he came up right off the page with 43 arcseconds per century. And it was said that he had heart palpitations when he saw that number. He was so excited by this result. And so that's a good start. Your idea is off to a good start when you can explain some half a century old anomaly. Okay, but he also made some other predictions. One, that the deflection of starlight by the sun, as light travels near the sun, it would be deflected. Now, Newton would have said the same thing. He thought of light as particulate. But Einstein said, yeah, that happens, but it should be actually about twice, or exactly twice the effect, because of the curvature of space in the vicinity of the sun. And so there was a very famous expedition in 1919 led by Sir Arthur Eddington to observe a solar eclipse and look at the patterns of stars around the limb of the sun to see how whether in fact the light was deflected by the Newtonian amount or by the amount predicted by Einstein, and it was in fact consistent with Einstein's prediction. And it's this event that made Einstein world famous. This is when he became more or less a household name. So he made a third prediction that time runs slower in a gravitational field, and it took a while before technology and the state of clocks could really check this result. It was confirmed first in 1960. It's now been measured to some very high precision. And if we didn't understand this fact, the global positioning system, navigation system, would have no chance of working because the clocks are sitting in outer space, and we have to understand the rate that clocks in space will run compared to those on Earth. And it turns out that your solution for your position on Earth would deteriorate within an hour if you didn't understand that general relativity. So Einstein, with his fresh new theory of gravity, turned it to the explanation of the universe. What could be better? Turn this big, deep idea about gravity onto the whole universe and see what happens. And he was dismayed to find out that his theory didn't permit a steady state static universe, which everybody at the time knew must be the way the universe had to be. So his general relativity required that the universe either expand or collapse. And it turns out then, and he introduced a cosmological constant into his equation for gravity to offset this, to make a repulsive term, to effectively stabilize the universe and allow it to be static. But then in 1929, Hubble and other astronomers announced the observed expansion of the universe, that galaxies appear to be receding from our own, and the farther one looks, the faster the galaxies appear to be receding. And so here's Einstein, and here's Hubble, and another guy, Adams, who was central to these observations. And Einstein is looking at this and saying, oops. And so he actually took out his eraser and removed this term in his equation, called it his biggest blunder. He could have predicted the expansion of the universe based on his theory for gravity, but he didn't. And had he done so, he would have been famous. He really missed this opportunity. Okay, so where are we today? General relativity has been subjected to a number of tests. Again, it's not something we just believe because Einstein said it. We have to test it. So far, general relativity has passed all the tests, but not all is well in the world, because the two fundamental pillars of physics, general relativity and quantum mechanics, do not get along. And so it's like there's talk of divorce, and it makes us physicists very, very nervous that these two aren't getting along. And so we suspect that something's not right. Maybe general relativity is not the correct theory for gravity. The ultimately correct theory of gravity is very useful. There's some insight there that surely is pointing us in an interesting direction, but it may not be the ultimate theory of gravity. So meanwhile, we've learned just in the last dozen years that the universe is, yes, it's expanding, but it's also accelerating in that expansion. Nobody really expected this, and it's actually brought back this cosmological constant that Einstein put in to have this repulsive effect on gravity. And so that's sort of back in vogue now. And it turns out that when we quantify using general relativity to describe cosmology in the universe, that we only understand 5% of the universe's content in things called atoms, things you could find on the periodic table, in stars and gas and dust, galaxies. But that 95% of the universe is in dark matter and dark energy, things we don't understand except for their overall phenomenology. We don't know what really makes it up. So all of these point to a real impetus to test, in fact, an imperative to test gravity. So the solar system offers a pristine gravitational laboratory. It runs without batteries for billions of years. It's the closest thing we have to perpetual motion. It's a very nice system. And this is a plot, it's a little hard to see maybe, but the Earth and the moon's orbit to scale. I also have here a scale model of the moon next to the scale, the same scale for the Earth. I would actually have to put these 30 feet apart to represent their separation. My arms will let me get to 6, so you have to imagine the rest. But the moon's orbit provides a way to check general relativity, because general relativity would predict 10-meter deviations from Newtonian gravity. And any theory of gravity had better be able to predict the shape of an orbit. And so what we can do is measure the Earth-Moon distance to map out the shape of the moon's orbit and ask whether or not general relativity is providing the correct prescription. And one example of this is in testing this equivalence principle, that the idea that any two objects fall at the same rate toward the sun. So it turns out the Earth, of course, is going around the sun. That's this blue arc. And the moon has an orbit that sort of loops around the Earth's. And if you draw its average position, if you sort of average out the wiggles, it's this dotted line. So if the Earth and moon are obeying the equivalence principle, they will fall at the same rate toward the sun. Their orbits will overlap. And we will effectively measure the same distance at full moon and at new moon, modulo the ellipticity and all the Newtonian effects that we understand. Whereas if the moon is falling faster toward the sun than the Earth, for instance, its orbit will shift and we'll measure a different distance at new moon and full moon. So that's a way that we can probe this equivalence principle using measurements between the Earth and the moon. It turns out that the Earth and moon do fall toward the sun at the same rate to within a part in 10 trillion. So lots of zeros in this percentage measurement. And the Earth-Moon system gives us a handle on another type of phenomenon, which is the Earth has its own gravitational energy in its gravitational field. And we can ask, does that energy, which has some mass equivalence, fall toward the sun like ordinary matter? So how does gravity pull on gravity? How does gravity of the sun pull on the gravitational energy of the Earth? And it turns out that if gravity couldn't pull itself by its own bootstraps, then the moon would see about a 13-meter shift. So these are things that we can actually look to test. Okay, so that all sounds very well and good, but not so fast, because what we really need to do is measure the distance between the center of the moon and the center of the Earth. That's what we need to describe in our theory of gravity, but we are confined to the surfaces in our equipment. And the surfaces are not stationary or rigid. So Earth rotates at 400 meters per second, or 900 miles an hour. And the moon is moving around the Earth at about 1,000 meters per second, or 2,300 miles an hour. And then the Earth and moon are going around the sun about 30 times that speed. So everything is in a state of motion. It makes it difficult to lay out a tape measure. Next, the Earth's surface is not as rigid as we like to think. It's very floppy. Just tides alone from the moon and the sun move the Earth's surface, the solid Earth's surface, by about 2 feet, peak to peak. And we like to think of the Earth as stationary and tides only affect the ocean, but no, the tides affect the solid Earth as well. And in addition to that, if you have a high pressure atmospheric system, a weather system, move in, there's a lot of mass there in that atmosphere, in that extra pressure. It puts pressure on the crust and deflects it by a few millimeters. So those things need to be understood. Even things like groundwater and California tides. We're sitting here in New Mexico. Water comes up on the California coast and pushes the Earth down, and even in New Mexico we feel the deflection. So we're not operating from a nice granite table here. Okay, so in order to do this measurement, we need some equipment on the moon, and fortunately the astronauts placed these reflectors. Here's Buzz Aldrin in the Apollo 11 mission, who placed a reflector on the moon, and that was the very first Earth mission, or sorry, lunar landing mission. And these reflectors consist of corner cubes. These are glass prisms like the one I'm holding here, and in fact this is the same size as the reflectors used in the Apollo reflector assemblies. And the Apollo 11 and 14 have 100 of these cubes, and the Apollo 15 has about 300 of these cubes. And these cubes have the property of having 3 mutually perpendicular surfaces, and light would come in this picture from the bottom, strike the 3 surfaces in turn, and emerge exactly opposite the direction it came in. So a bike reflector works by a similar principle. And that means we can shoot a laser at the moon and the light will come back to us on the Earth. So where are the reflectors? The Apollo reflectors are arranged in this somewhat triangular pattern. Well, not somewhat, it's perfectly a triangular pattern. And then there are 2 Soviet-landed rovers, Lunokhod 1 and Lunokhod 2, that also bear corner cube arrays. Okay, so we started a project to try to do a factor of 10 better than all the projects that came before. Lunar ranging has been going on since 1970 and has provided many of the best tests of general relativity. We saw an opportunity to extend this another factor of 10, and our first task was to develop a clever acronym. You have to start there. So it turns out we're using the Apache Point Observatory in New Mexico at 9,000 feet, and our technique is lunar laser ranging, so you just demote the R, come up with an O, and NASA cannot resist funding a project with the acronym Apollo. And the National Science Foundation also chips in, and we're co-funded by those 2 organizations. But that's the easy part. The hard part is building a state-of-the-art apparatus that can achieve 1 millimeter range precision to the moon. Okay, so how does the whole scheme work? Here we have an animation of a telescope on the Earth, reflector on the moon. We're sending pulses out of the telescope. Every time it flashes red, a pulse is sent out. And the pulse takes 2.5 seconds to get to the reflector and back to the Earth. So I've shown it slowed down here quite a lot. We're actually flashing the laser 20 times a second. As the pulse emerges from the telescope, it immediately encounters the Earth's atmosphere. And the Earth's atmosphere makes that beam as carefully as we collimate it, so it's parallel. The Earth's atmosphere introduces distortions, and the beam begins to spread at 1 arc second, which is a very small angle, 1/3600th of a degree. But by the time we get to the moon, that's 2 kilometers across, and we're hitting something the size of a suitcase. So most of the light that we send just goes thud on the lunar surface. The light that's lucky enough to hit the reflector starts the return journey, but only 1 out of 100 million of the photons of light that we send up to the moon are lucky enough to hit the reflector. Of those that do start to return, the corner cube prisms introduce a diffractive spread to the returning light. And that's even greater than the spread from our atmosphere, it turns out. So we end up with a 10 or 15 kilometer footprint back at the Earth. And our small little 3.5 meter telescope barely scoops up any of that. In fact, it's about another part in 100 million. So it's a very challenging enterprise with a lot of signal loss. We have about 50 pulses in flight at any given time. Okay, so what does it look like? Well, the Earth site is in New Mexico on a mountaintop. There's a 3.5 meter telescope. There's the mirror. This is the 2.5 meter telescope that does the Sloan Digital Sky Survey, if you've heard of that. And we have our laser mounted on the telescope here. There are a couple of people here for scale. Not necessary for the equipment. Okay, we have the laser mounted on the telescope here, and we call this the Utah box, and I'll leave it to your imaginations as to why. And here's where the primary mirror sits, and this is the secondary mirror. This is a view of the laser emerging from our port, heading toward the tertiary flat mirror. It goes from there up to the secondary mirror, spreads out then to hit the primary mirror and coats it in nice green, and then it gets collimated and moves up toward the moon. So we waste a lot of photons. I mean, we are running this telescope in reverse. A telescope normally takes photons from the sky and collects them for a detector, but we feel like astronomers have been too greedy all these years, so we're donating a lot of photons back to the universe, mostly the moon. Our loss rate is quite high. We we get 1 photon back for every 10 to the 18 roughly that we send. And so I wrote out all the zeros just to be impressive. So this means that if you represent 1 photon by a grain of sand, 1 millimeter across, we're launching about a cubic kilometer of sand with each pulse 20 times a second, and we get 1 of those grains back. So we lose almost everything. How do we picture even 1 cubic kilometer of sand? Well, if you take the California coast and take 1,000 kilometers of coastline with sand 10 meters deep, 30 feet deep, and about a football field wide, that's how much sand we're talking about, and we get 1 grain back from all that sand launched. Okay, and we have to, even to do that, we have to be incredibly good at pointing. We have this 1 arcsecond beam width, so we have to point it to within 1 arcsecond. And 1 arcsecond is the width that a car would span 400 kilometers away. That's from here to Las Vegas. Or it's also the scale of a quarter, 5 kilometers away. So it's a very tiny angle. And meanwhile, everything is on the move. The moon is moving across the sky at 15 arcseconds per second. And so as we take aim on the moon, we have to do so very, very carefully. And meanwhile, the distance that we're trying to measure to millimeter precision is changing by as much as 400 meters a second, mostly from Earth's rotation. To make it worse, we're doing this juggling act. We've got 50 pulses in flight at any given time, and we do this with our eyes closed. And by that, I mean that we have this photon-sensitive detector, avalanche photodiode array, and it has to be sensitive to individual photons of light, which means that looking at the bright moon is the last thing it wants to do. Flooded with light, it would be rendered useless by this bright light. So we have to keep its eyes closed almost all the time and only open it right when we expect a pulse to come in. So that's like juggling all these balls in the air and only opening your eyes right when you expect the ball to hit your hand. The one that you threw 50 times ago, nonetheless. Okay, and so what is this 100 nanoseconds? That's how long we open up our detector. Light would go about 100 feet in 100 nanoseconds. It's a foot per nanosecond, but we don't have much intuition about light speed. So what about a fast bullet? A fast bullet would go about the width of a human hair in 100 nanoseconds. So that's as long as we're opening up our detector. And so that means we have to predict when that return is going to come back, because we're only going to open up for a short amount of time. If we open it at the wrong time, we get nothing. We have to open it at the right time. And we have to keep updating this prediction, because from one shot to the next, even a 20th of a second changes, the geometry changes enough, our prediction can change by more than the width of our detector gate, more than 100 nanoseconds. So every time is different. We can't just do the calculation once and call it good. We do it 20 times a second. Okay, but we've done quite well. Let me just show you some of what the results look like. So I'm plotting here the offset from our prediction. We're predicting when this thing should come in. This is shown in nanoseconds. And we have background, which you might see here as little specks. They don't show up terribly well. Little specks that are randomly timed, because the background, the light from the moon, doesn't care when, the photons don't care when they were emitted or when they arrive. They just come whenever they want. Meanwhile, our signal comes at a very special time relative to our prediction. In this case, it's a few nanoseconds early. We don't worry about small offsets. And if you make a histogram of these results, you get something that looks like this. It's a big, thick slug of returns. In this case, we got almost 7,000 photons in something like 4 minutes of time, 5,000 shots. And here's the distance that we measured for this particular instance. We just picked some characteristic time in the middle of the observation, because the distance is changing all the time. But we characterize a representative time, and I like to write out all the digits because it makes me feel like we've done something. So we're measuring to something like millimeter precision. Now, we have achieved record rates that are 70 times better than anything that's come before our project. So we're operating well in excess of anything that came before. Our typical nightly measurement precision is about 1.5 millimeters. So we really are getting to that paperclip width on a routine basis. we can actually range at full moon now. We have enough signal that we can get the return back at full moon, which is something that was off limits for the last several decades. Other devices couldn't do this. And one thing I think is really cool is we can verify the size, shape, and orientation of these reflectors because we have a local corner cube in the telescope that sends back some small portion of the light that's going out. It intercepts the light and sends it back through the system, and we get basically a start time. When did the light leave the telescope? It's a very important measurement for our overall measurement goal. And it's very narrow, notice, while as this thing is fat. And the difference is the reflector. The reflector is this rectangular thing that, because the moon goes through this sort of libration pattern, it changes its angle very slightly, we get different angles. And so the light from the laser that hits the reflector gets spread out a little fatter when it comes back. And based on the physical size of the array and its orientation, we can predict what the shape should look like. And as that pattern changes, we see it looks exactly like it should. So the lunar reflectors are, as advertised, the right size. And the astronauts oriented them to within 1 degree of the optimal position. So they did quite a good job. Okay, one other facet of what we're doing is we are taking sage advice. We're fighting gravity with gravity. We are, on the whole, we're trying to make a measurement that will tell us something about general relativity. So we're trying to learn about gravity. And one of our tools that we use in our arsenal is a superconducting gravimeter, which was invented here at UCSD by John Goodkind. And we have this bolted to the concrete telescope pier that the telescope's mounted on. It goes into bedrock. And this consists of a levitating superconducting sphere that we hold 4 degrees above absolute zero, liquid helium temperatures. And we're basically judging as gravity pulls on this sphere, we judge how strong that pull is. And so this is so insanely sensitive that if the sight were to move up by 1 millimeter, this gravimeter would say, hey, wait a minute, gravity is a little weaker up here. I must be farther from the center of the Earth. So it's that incredibly precise. And so here's 1 month's worth of record from our gravimeter showing tides. These are the pattern that you're seeing here is from the lunar and solar tides pulling on our gravimeter. And it looks a lot like tide tables that you would look at for high tides, low tides in San Diego. The scale for this particular month is about 20 inches of vertical motion for our site. So it's very important that we are measuring this and understand this. But hidden in here, we can't really see it, but underneath the tides, we have other motions of the site from groundwater, from atmospheric pressure, from coastal tides on California's coast, pushing the site around. So we're getting some measurement of that through this gravity probe. When you have a device this sensitive, you're bound to see some interesting things. Like one day, over the course of an hour, I saw 3 unequal steps in gravity. Each one, gravity got a little weaker. And it turns out that they have these giant concrete blocks that once a year they use at the observatory to load test their crane before they pick up the expensive telescope parts that, and that you don't want to find out that way that your crane doesn't work. So they use these concrete blocks, and the gravimeter sits on the other side of this concrete wall, roughly here, and I can even tell that they moved this one first because it's farther from the gravimeter and that was a smaller step. And then they moved that one, and then they moved that one. Okay, and the next day they all came back into place. So we can also see funny things through gravity, like every time the telescope dome rotates, the gravity signal from the dome imprints on the gravimeter signal. It's small, and we can take care of it. We can subtract it, but it's there. Other things happen, like after the earthquake in Chile in late February of 2010, the whole Earth was ringing like a bell with a 20-minute period. For something like a month, we saw these wiggles continue. So I'm learning something about geophysics in the process. Okay, so one of the surprises that we've found along the way is that the reflectors aren't working as well as they should, or we expect them to. So if we represent lunar phase across here, so full moon is in the middle, new moon through quarter to full and last quarter and so forth, and we expect the reflectors to operate at 100%. Naturally, that's what we'd expect these to do. What we actually get, we get something like 10% performance, and at full moon, it dips down to 1%. And so it's a factor of 10, even if you don't believe this, we're definitely seeing a factor of 10 hit at full moon. So the reflectors get sick. It's not just that the background is higher, the actual signal goes down. And like I say, for a while we joked about this and thought it was just we are getting unlucky, and the conditions of the nights tended to be poor when we were at full moon. But pretty soon it was a fairly obvious truth that we had to deal with. So what's going wrong? I think it's very likely dust. Dust can get kicked up on the moon from electrostatic levitation, from photoionization from X-rays and UV from the sun. It can charge up dust grains, and they can repel each other and float around. And solar wind can also deposit charge on the moon and move the grains around. So normally, we'd have light coming in, hitting the back faces of the reflector and coming back out. So that's all well and good. But if you put dust on the front, the light comes in, gets attenuated, and attenuated again. So it's a double whammy, and you get much less light coming out. Okay, so that explains our overall factor of 10 across all phases. What about this weird full moon effect? What's happening there? These arrays are oriented deliberately to point at the Earth. The astronauts did that on purpose. Okay, well, at full moon, if you think about it, if you're at the moon and you're looking at the Earth, the sun is on the other side of the Earth. Not precisely so, or you'd be in a lunar eclipse, but it's somewhere off in that direction. And so light can come straight down this recessed tube and hit the reflector straight on at full moon. And when all that sunlight gets dumped onto a layer of dust, and the dust was not part of the design consideration for these reflectors. They were designed to be clean. When this light is dumped onto the dust, it will warm up. Now, it doesn't necessarily get red hot, but it gets warm, okay? And when it gets warm, you've got a warm front surface, and it's cooler in the interior and cool at the vertex. And so a light ray that comes in near the center of the corner cube and penetrates deep into the corner cube down to the vertex goes through cool glass, and that turns out to be quick. That goes faster. Then the light that comes out near the edge hugs a path that stays near the surface where it's warmer. And so that goes slowly. And the net effect is that light in the center gets out sooner than light at the edge, and the light that's coming back is not in a plane wave anymore, it's in a spherical wave, and it's diverging. So by heating up this cube, you distort the refractive properties of the cube, and you spread the beam out so it's much larger on the Earth than it ordinarily would be. And it turns out that thermal modeling of these cubes shows it only takes about 4 degrees C, or about 7 degrees Fahrenheit difference between the surface and the vertex to cause a factor of 10 reduction in your throughput. And that's not a huge effect. I can easily imagine that would happen when dust is coating the surface. Okay, we will have an opportunity in December 2010 for a spectacular eclipse that's almost overhead at the site. It's actually a good eclipse for all of North America. And it basically gives us a light switch. So while the atmospheric conditions are the same and the observing conditions are all the same, we get to turn off the sun and see, do the reflectors recover? If so, over what time scale? Is this recovery consistent with a thermal problem in the corner cubes? And then we get the sun to turn back on after the experiment's over. So that should be a very powerful test of these ideas. Okay, and finally, I'm going to tell you about the fun that we've had finding the missing reflector on the Soviet Lunokhod-1 probe. So Lunokhod-1 carried this 14-element corner cube array. It's of a different design, but similar concept, with a similar response to the Apollo arrays. And so it's sitting here on the front of the rover. And so the rover was solar powered. It would maneuver itself around during the daytime. Actually, there were commanders on the ground telling it where to go. And it was, by the way, the first ever robotic deployment to a planetary surface other than the Earth's. And this was in 1970. It was a very successful mission. It traveled a total of about 11 kilometers across 11 months, which on the moon is called a day. And it would stop during the nights oriented toward the Earth, so that this reflector was pointing at the Earth, and attempts would be made to laser range to it back in 1970, 1971. The only published positive results were from December of 1970. Both the French and the Soviets managed to get good range measurements, but these weren't published in any detail, not enough that we could get coordinates out of it. Subsequent attempts didn't pan out, so nobody was really sure what happened to this array or where it had gone, what its condition was, etc. So we've got this incredible new system. Let's just go nuts and blast at it and see what we can get. Okay, it sounds easy, but it's actually rather unlikely that we would find it, because the uncertainty of its position on the moon was 5 kilometers. Okay, well, we've got a 2-kilometer beam. Seems like it wouldn't take that long to cover a 5-kilometer uncertainty. That's absolutely true, but that's not our biggest limitation. Our biggest limitation is the fact that we operate with our eyes closed, like I described before. So we only open up our detector for this 100 nanosecond period, and we have to know when we should open our eyes. And if you imagine, let's just remove the pointing issue, that we send a laser pulse to the moon and we're only looking for light that would come back after a certain delay. Well, that really is asking the question of, when does this laser pulse, how does it slice the moon? Where, you've got this spherical moon and a laser pulse that's hitting it, and there's some circle where that laser pulse intersects the moon at some instant in time. Okay, so we have this circle, and it turns out for our 100 nanosecond gate at the position of Lunokhod 1, that's about 20 meters wide. So our real search area is 2 kilometers across the beam by 20 meters wide. And that's a much smaller thing. You'd need 2,000 different experimental setups to cover the entire 5-kilometer search, and so it makes it very unlikely that we'd find it. Okay, so can't we just follow breadcrumbs? Because after all, the operators of this rover knew where they were driving it, and they had pictures of craters that they would encounter, and they knew how far they drove and what direction, etc. So they actually built up a map of where the craters were. So you should be able to look at images of the moon and match the craters that they found to the craters that the image shows. That sounds great, but it turns out that the imaging was not really good enough to identify the crater field. There were a few speculative associations, and we went on the best of those, and it turns out that that picked out a spot that turns out to be 4.5 kilometers away from where we now know the rover to be. We searched on and off for a couple years. We had no chance of finding it in hindsight. So what changed is the Lunar Reconnaissance Orbiter. This is a device that was launched in June of 2009, and among other things, it was equipped with a high-resolution camera, a laser altimeter, and a corner cube array also mounted to it. And the corner cube array is interesting. Only our experiment, Apollo, has any chance of getting a return from this corner cube array. And because of that, we were motivated to expand our gate width, this 100 nanosecond gate width, to 800 nanoseconds to give ourselves a little more freedom in searching, even though the background might sort of be a limiting factor. And by the way, this isn't Star Trek. You don't just press a few buttons and suddenly you've got 800 nanoseconds of capability. It's a few months of design and testing. So anyway, we had this wider gate, but most importantly, Lunar Reconnaissance Orbiter actually took pictures of this thing. Okay, so it found the lander, that's arrowed here, and it found the rover. And you'll notice all the craters are lit up from sort of the, on this image anyway, from the lower right, so that they're bright up here and dark down here, but this is different. It's bright on the lower left and dark on the lower right and dark on the upper left. Okay, so it's something that sticks up. All right, just for fun, if we go back to this original image I showed you, I'll now point out where this is. It's right here. Okay, it was there all along. Did anybody see it? Okay, one, maybe two. Okay. So also, if you zoom in around here, you actually see the tracks, parallel tracks from the rover as it left the lander. Okay, so this is great imaging. It's wonderful stuff. By the way, if you get a chance, look at the Apollo 12 landing site from the LRO. You see footpaths that the astronauts walked around. It's fantastic. Okay, also it had this laser altimeter, and this laser altimeter is measuring the distance from the spacecraft down to the surface through a similar technique of laser ranging, just off the dirt, not corner cubes. It's a much harder job in some sense. They made two tracks about 1 kilometer to the left and the right, east or west of the rover, and if we plot the radius from the center of the moon of these tracks, what we see is that both tracks are more or less on top of each other, and this is only 5 meters from here to here. And so that means that there's not much east-west slope. And more or less they're flat in the north-south direction. So this is a flat plane. We have the altitude to about 5 meters, and from the imaging we have the latitude and longitude to 100 meters. So now we're talking. We're not dealing with 5 kilometers anymore. We're getting down to small numbers. And this made it very straightforward, actually, for us to find it. And in fact, on our first favorable opportunity with good weather, we started a run right here, and immediately we're seeing this line right on the edge of our gate. We open up our gate to 500 nanoseconds. We're getting kind of stomped by background. There's a lot of background here. But we saw this really bright signal on the edge, and we're always suspicious when we see something right on the edge. It could be some artifact of our instrument. And so it's about 270 nanoseconds off from our nominal prediction, right on the edge. But then we started moving the gate. We changed our timing, changed our prediction a little bit. And we see the gate making these steps, but the signal stays right where it should be. So that's what a real thing should do. It didn't follow the gate. It was a real thing. This was our first ever 8-minute run on Lunokhod 1, yet we got about 2,000 photons out of it. This beat by a wide margin the best that we'd ever seen from its twin on Lunokhod 2 after years of working on it. So right away we knew we had something good, and at the time I said, you know, this rover has a lot to say after 4 years of silence. But the best quote came from a colleague at the Apache Point Observatory, Ed Leon. Your discovery gives hope to all of us who lost something during the 70s. I think that works on so many levels. It's a really great way to put it. Since then, we've nailed down the position through different measurements at different times. The moon is oriented in different ways slightly. And so we have these gray bands of measurement that intersect at some central point. And these blue ellipses represent 68%, 95%, and 99.7% confidence limits. And this scale is in centimeters now. And I measured in this auditorium beforehand so I could scale this graph to real physical size. So this is how well we've determined the position of this rover. Used to be unknown to 5 kilometers, and now we've got it to a few centimeters. So that's very gratifying. And it's a lot of fun, but there's more to it than just the fun. This reflector happens to be the most sensitive of all the 5 reflectors to lunar orientation. And that's because it's near the lunar limb. If you have a reflector right at the center and you adjust the moon's orientation a little bit, the range to that reflector doesn't really change much. But over on the limb, that range can change a lot when the orientation changes. So this is the farthest away from the center. It's the most sensitive to orientation. Why is that important? Because if we want to understand where the center of the moon is to test gravity, we really need to know how the moon is oriented so we can convert measurements to the individual reflectors into an effective measurement at the center of the moon. So it's going to be very important for that. It's also very good for understanding the lunar interior. And having 5 reflectors now also lets us measure the distortion, better measure the distortion of the lunar surface due to tides from the Earth. So that's very nice. The fact that its return is much stronger than its twin, Lunokhod 2, is still something of a mystery to us, but we'll take it. It's about as strong as the Apollo 11 and 14 reflectors. It turns out to be usable during lunar daylight, which its twin, Lunokhod 2, is not. So it's useful more of the time, and we have a new best friend. Okay, so let me just close by saying that I personally feel very privileged to be able to work on a fun project like this that answers questions fundamental to science. This is basic research, I think, at its best. And I think that in today's world, when we have fewer frontiers, physical frontiers to explore, science is always going to offer frontier. And so it's a great place for explorers to mess around in. So, and we're not really smart enough to understand the impacts of the basic research endeavors that we pursue. A few examples, I already talked about general relativity and its importance for the global positioning system. For decades after general relativity was formulated and understood, nobody really foresaw that application. Now it's in almost every car. Most of us wouldn't be able to get anywhere without it. Lasers were once thought to just be a cute demonstration of quantum mechanics. I think people called it a solution looking for a problem. And look at it now, DVD players, laser pointers, it's universal, it's everywhere. And the inventors of the transistor were thinking about, I guarantee you they were thinking about transimpedance properties of electronic devices. They're not thinking about computers or iPhones. So it's really important that we follow these basic research directions wherever they might lead. We're not smart enough to foresee the impacts, but let's hope we're at least smart enough to continue these kinds of ventures. And again, I'll just say I feel very lucky to be able to play in this world of basic research.